Well, the request has been made to liven these videos up a little bit, so I thought I'd do oxidation reactions as an astronaut. Actually, it's way too hot in here. But oxidation and reduction reactions are fairly important. I have to admit they're not my favorite, but we will learn a little bit about them in this chapter, and then later on we get to do a whole chapter called electrochemistry. Yay! Alright, so for right now, there's not really a whole lot to learn that you probably didn't already learn in Chem 1. This hurts. Alright, it's meant for a smaller head than what I have. Okay, so oxidation is when an atom loses electrons, whereas reduction is when an atom gains electrons. It seems kind of weird to call it being reduced when it's gaining something, you know, and if you gain weight, you don't say your weight was reduced, but it's because electrons are negative. So when an atom gains negative electrons, its charge actually goes down. And since its charge goes down, we call that being reduced. Okay, there's a way to help remember this. Oil rig is one of them. Oil, O-I-L, oxidation is loss. Rig, R-I-G, reduction is gain. The other way I like to remember it is Leo the lion says grr. Leo loses electrons, oxidation, and grr, gains electrons is reduction. So oil rig, Leo the lion, whatever works for you. Okay, here's a little short video clip I found showing exactly what's going on in a redox reaction.
When zinc metal is exposed to oxygen at high temperature, it reacts to form zinc oxide. Electrons are transferred from zinc to oxygen, creating oxide and zinc ions. We say that zinc has been oxidized. The oxidation of zinc by molecular oxygen is an example of an oxidation-reduction reaction. More generally, oxidation corresponds to a loss of electrons. Zinc is oxidized because it loses electrons to the oxygen. On the other hand, oxygen is said to be reduced because it gains electrons.
Alrighty, so a key thing to remember with any oxidation-reduction reaction is that one doesn't happen without the other. You can't have an atom gaining electrons if there's not another atom in that reaction that's losing electrons. So one cannot occur without the other. One atom or substance, it could be a polyatomic ion or something. It doesn't have to be a whole, just one atom. But a substance is losing electrons and becoming oxidized, while the other substance is gaining electrons and becoming reduced. All right, so here's calcium being oxidized by the oxygen in the air. Your metals, in a simple reaction between a metal and a non-metal, it's always going to be the same thing. Metals become positive, right? We know this. So that means they were oxidized. And then non-metals get negative charges. So those were reduced. So metals are oxidized and non-metals are reduced. And you're just simple reactions between individual elements like this one. All right, and a bigger version of the picture from before. All right, so to figure out oxidation numbers, it's basically, if you know how to write formulas, you've got a majority of this down. Okay, the oxidation number is very, very similar just to figuring out the charge. So, some rules. First of all, pure elements have no charge. So the gold in my ring, the oxygen floating around in the air, none of these elements have a charge yet because they haven't reacted with anything. So if you see a pure element by itself, even if it's bonded with itself, you know, like O2, the charge is 0. Then if it's a monatomic ion, just like a sodium ion or an oxygen ion, those are the same charge as always. Okay, the oxidation number is going to be the charge you worked with all through Chem 1. So oxygen's -2, sodium's +1. All right, nonmetals can get a little weird, though. Okay, if the nonmetal just hooked up with the metal, well, then the charge will be its negative charge, like you're used to it having. But it can be weird once polyatomic ions get involved. So I'll show you what I mean by that in a second. We can always assume that oxygen is -2 unless we're talking about sodium peroxide or hydrogen peroxide. in that less stable, more reactive situation with peroxides, the oxygen's -1. So unless it's specifically called peroxide, you can just assume the oxygen is -2. Now, hydrogen can go either way. He can be +1 and lose an electron, or he can be -1 and gain an electron. How do you know? Well, you have to see who he's bonding with. Like in HCl, hydrochloric acid, the H is positive and the Cl is -1. But in, say, sodium hydride, NaH, the sodium's +1 and the hydrogen's -1. So the position of the hydrogen can give you a clue. If he's written in front like a metal would be, he's positive, and if he's written in the back half of the formula like a non-metal would be, that's negative. All right, fluorine's always going to be -1. The other halogens tend to be -1, just like, they were when you learned to write formulas. But they can do weird things and have even a positive oxidation number when they're in oxyanions, meaning polyatomic ions with oxygen in them, like sulfate or nitrate. Okay, now, we don't have a rule for every single element on the table, which is actually a great thing, because that would be impossible. So a lot of times you kind of just have to deduce what a particular element is doing by using the fact that the sum of all the oxidation numbers in a compound is going to be 0. So in sodium sulfate, Na2SO4, we know the sodium's +1. We know the oxygen's -2, but what the heck is sulfur doing? Well, use your math, okay? There's got to be an equal number of positives as there are negatives for the whole compound to be neutral. All right, now if you're just trying to do a polyatomic ion and figure out, okay, sulfate, what charge does the sulfur have in sulfate? Well, then the total of all the oxidation numbers needs to be the same as the charge on the ion. So if it's a -2 polyatomic ion, you're going to need 2 more electrons, 2 more negatives than you have positives. So I'll show you some examples like that. We'll do this one in class. This is in your sample notes. Now, H2S, okay, H is in the front. So when H is in the front, he's +1. So we have 2 of them. So that means we have 2 pluses, so the sulfur must be 2 minus. What about S8? Well, that's a pure element. It's one of the many allotropes of sulfur. So the charge is 0 because it's just pure sulfur. All right, SCl2. Well, chlorine's -1 usually, and so that means we have 2 negatives. So the sulfur must be 2 positive here. Then in the sodium sulfite, well, this whole thing is neutral, right? So I know sodium's always +1, so I have 2 positives. I know oxygen's -2, so I have 6 negatives. So if I have 2 positives and 6 negatives, what do I need to make there be no overall charge? Well, I would need 4 more positives, right? For a total of 6 positives. So the sulfur here is +4. Now, what if you just had a polyatomic ion, just sulfate? What would you do there? Well, I need to have 2 more negatives in here than I have positives. So I have 4 O's. Each O is -2, so that's -8. What must the S be in order to leave 2 negatives overall? So if I have 8 negatives, then my sulfur must only be 6 positive. All right, if you need a little bit more elaboration on that, you can pause the video right here and read through those. These are also in your textbook as well. All right, we'll do those in class. Okay, now I'm going to stop right here because this is the end of just figuring out oxidation numbers. We will pick up with actually doing reactions in the next video, doing redox reactions. In the meantime, let's see. Oh, hey, you like this painting back here? In case you noticed. Okay. I painted this. I taught myself how to paint last year. And I've got 2 like this, 1 over each end table. I'll show you a different one next time. Okay, now it's really crooked, but I'll fix it in a minute. Bye for now.